Lynchburg Foundry proudly brings you this issue of the Science Screen Report. The nation's leading independent foundry has been a growing part of the Lynchburg community since 1896. We manufacture quality engineered castings using 2800-degree molten iron and automated equipment to shape intricate parts. Chemical and physical analysis form the backbone of Lynchburg's quality control program. Precision castings are used in a variety of industrial and consumer products. Experience, technology, quality, and the foundry's greatest asset, people, have combined to make Lynchburg Foundry the leader in its field. And now, the Science Screen Report.
The Science Screen Report, bringing you each month the latest in science, engineering, and medicine, made to help solve the problems of modern life. For billions of years, the sun has provided heat and light to planet Earth. Today, solar energy is being harnessed by science and technology to regulate temperatures in buildings, on farms for warming and drying crops, in industry for refining ores and other tasks using heated water, and via enormous arrays of focusing mirrors to collect heat to run turboelectric power stations. What follows is a report on new advances in solar energy research and applications. In recent years, scientists and engineers have begun to apply the sun's potential to solve the energy problems of our planet. At the Solar Energy Applications Laboratory at Colorado State University, solar heating, cooling, and air conditioning systems are under development. To test and compare these systems, 3 residential structures were built on campus. One house has an all-air solar system. This all-air system functions in several ways. In one, warm air from the collector is piped directly to the conditioned space to heat it, as required by the thermostat. If this hot air is not needed, automatic dampers directed to a rock box, where the heat is stored for later use. When the thermostat calls for more warmth, the stored heat is moved from the rock box to the conditioned space by circulating air through the heated rocks. If there is not enough hot air, a conventional system goes on automatically. The solar system may also heat hot water for domestic use via a heat exchanger coil. In the first test house, the all-air system is also used for cooling. Cool night air drawn into the system cools the stored rocks. When temperatures rise during the day, air is circulated across the cold rocks, where it is cooled and then transported to the conditioned space. The other 2 houses at Colorado State University utilize hydronic solar systems. The only difference between the 2 is the type of collector used. The hydronic system works essentially the same way as the air system, except that instead of air being heated in the solar collectors, a non-freezing liquid is heated. This liquid goes to a heat exchanger, where it heats the tank of water. The hot water is then pumped to an air duct heating coil. Air is blown across the coil, heated and circulated to the conditioned space. For cooling, Stored hot water is pumped to an air conditioner where this energy operates the unit. Water from the storage tank passes through a heat exchange, providing domestic hot water. When there is insufficient solar energy, conventional backup units take over and supply the required hot or cold air or hot water. Modern industry's belief in and support of solar power research is exemplified by the new sheet metal trade school in Detroit, Michigan. The building includes both solar space heating and domestic hot water systems, so to both teach apprentices about solar systems and provide new knowledge on how to apply them more efficiently. In Canada, the National Research Council is engaged in several projects testing the practicality of solar-heated homes. Most residential and commercial buildings here are maintained at temperatures already attainable by solar collectors. Farming also takes energy, and researchers are already improving food and fiber production by applying solar energy to aspects of agriculture. One promising effort employs stored solar energy to heat greenhouses, a project underway at Rutgers University in New Jersey. The water is first warmed in this plastic container, then flows by gravity back to the greenhouse to be stored underground. The stored hot water warms the building after sundown or on cloudy days, fostering plant growth. At night, curtains are drawn around the plants, reducing the rate of heat loss. Solar heating of buildings for animals is also underway. In Mississippi, engineers are using two systems to heat a poultry house. One involves direct warming of the air used to ventilate the house. The other generates warm water to provide energy at night and on cloudy days via a radiator. A plastic duct with holes in it distributes the heated air. A dairy farm in Maryland also uses collectors, 1,000 square meters of them, to meet most of its heating requirements. The heated water may be used at once for sanitation and temperature control, or can be stored in an underground silo. The final goal is a simple, durable, economical system that could be used on almost any farm. Agricultural applications include warming water for animal and dairy equipment sanitation, drying crops, and heating buildings for animals. At this ranch in the Arizona desert, solar-powered irrigation is being evaluated. 9 banks of solar collectors follow the sun as it moves across the sky. The energy gathered is used to drive a turbine pump, which delivers 50,000 liters of water a minute to crops on these arid acres. Such systems should prove valuable in croplands with unreliable rainfall, as well as in dry regions. One of the most promising applications of solar energy is the use of sun-warmed hot water in industry to refine minerals, purify chemicals, or in other processes. Recently, a major study of trapping and collecting solar heat using shallow solar ponds filled with water was begun at Lawrence Livermore Laboratory in California. The first step was to assess various alternate designs. Full-scale field evaluations were made in New Mexico. An abundance of sunshine, a dry climate, and flat topography provided ideal test conditions. Each morning, water is pumped into the containers. Solar heat penetrates the cover and is absorbed. The absorbed heat sets up water circulation currents, while insulation reduces energy losses. By late afternoon, the water reaches maximum temperature, whereupon the hot liquid is piped to a central container for use in local mining operations. Such ore refining represents only one of the hundreds of industrial uses for solar heated water. Data on the water temperatures, including temperature and evaporation changes, is collected by sensors and recorded in these trailers. 10% of world energy consumption is for heating below 100 degrees Celsius. In the future, major industrial complexes may be completely supplied with energy by such solar heat collectors. Solar energy may also provide large amounts of electrical power. The mirrors of New Mexico's Sandia Laboratory Power Tower experiment now focus enough heat to generate 5 megawatts of electricity, enough to meet the needs of several thousand people. The New Mexico experiment is a forerunner of a 10 megawatt solar electric power plant being built in California. 1,900 computer-controlled mirrors will collect enough solar heat to provide electricity for a small town. Still other solar technologies are being pioneered, like these solar photovoltaic cells, which convert sunlight directly into electricity. At Sandia Laboratory, a new test facility is being used to develop more effective photovoltaic cell systems. One approach? Plastic lenses that focus more sun power onto each individual cell. In the future, low-cost production of materials that convert sunlight directly to electricity could lead to many new applications. Roof-mounted cell arrays on future homes could provide cooling, heating, and electricity. Agricultural complexes might also be designed to be irrigated by solar photovoltaic cells. While very large amounts of electrical power could be produced using huge banks of solar cells. Together, these and other solar energy research projects are finding new ways to use the power of the sun to help solve problems on Earth.
Lynchburg Foundry has been proud to bring you this issue of the Science Screen Report to further your understanding of science, engineering, medicine, and technology.